Hi folks, let's talk about Bazel and how to get started with it. Bazel is a build system, just like CMake, Maven or Gradle. What makes it special is that it's built for really large code bases. Think massive monorepos with hundreds or even thousands of subprojects. But don't worry, we'll start small. My main goal today is to help you understand how Bazel works. Once you get it, working with real projects becomes more straightforward. Bazel can be overwhelming at first. It's easy to get lost in whatever documentation or AI tell you to do. But once you know what's going on behind the scenes, everything gets a lot easier. For this video, I will use IntelliJ IDEA with a new Bazel plugin. So let's create a new Bazel project and see what's in there. Alright, here I have an IntelliJ IDEA welcome screen. We want to create a new project. Let's call it Bazel Demo. It's a Java project, and also let's make sure that we use Bazel as a build system. Create. It is fast to generate project files, but then it takes some time for Bazel to do an initial sync and for IDEA to get all the necessary information from Bazel and present the relevant project components. Once it's done, we can look around. We have a Bazel tool window. There are some targets here. We'll talk about them later. There is the MODULE.bazel file with some part of a project configuration. We'll get to that as well. There are some source files, and you can see we have a standard Maven directory layout. Build.bazel file, main file, Java, okay. We can run it. It works, hello world, great. There are also tests. We can run them as well. Passed. Alright, it's time to look at the Bazel configuration and talk about the main concepts of Bazel. IntelliJ IDEA calls Bazel under the hood. Where did it come from? Well, I have Bazelisk installed on my machine. IDEA downloads it if it's not available. The exact Bazel version is mentioned in the .bazel version file. It's a good practice to have a Bazel version fixed and checked out in the repository. Note that I don't need to install that particular version manually. Bazelisk will download and run whatever version is requested. We also have several Bazel configuration files, including MODULE.bazel and build.bazel. These files are written in a subset of the Python-like Starlark language. There are other types of Bazel configuration files which are allowed to use fully featured Starlark. We'll get to that later. The project we're looking at here is a repository or main repository, the one where we run our Bazel commands. Bazel uses the term repository, or repo for short, to denote any collection of files used in building software. Besides the main repo, we also need many other repos, including those with tools, for example, compile executables, and external code dependencies. This project is also a module, which is a named and versioned unit of the Bazel dependency management system. We declare dependencies in Bazel by referring to modules, and as a result, get access to the corresponding repositories with files. There is no one-to-one mapping between modules and repos. A single module dependency can bring us many external repositories. Note that this module-based dependency management is called Bazel mod. Bazel projects used to have the workspace file, but the new system is much better and is used by default in the latest versions of Bazel. These days, we use the word workspace to denote the collection of all the repositories required to build our main repo. Let's look closely at the module.bazel file. It starts with a module declaration, setting the module name and the version number. In Starlark terms, we call a method to set certain properties of a module. We also declare a couple of dependencies of this module. Our project is a Java project, so we need to teach Bazel how to work with Java and external dependencies for Java code. Teaching Bazel to do something means providing a set of rules on how to work with certain files. The rules Java module provides exactly that for Java sources. So we add a dependency to a module that brings us a repo with those rules. The other module, rules.jvm external, is a bit different. In addition to bringing to scope some repo, it allows us to define and create a new repo containing the required external JVM libraries. Note the difference. Instead of simply attaching a repo related to a module, we ask to create a repo with some specific content. To describe what we need, we use a module extension mechanism. We request access to a module extension called Maven via the useExtension method, and then tag this extension with a description of the specific repo we need, a name, a list of required dependencies, and their source. The parameters here must be recognized by Maven, so we use the Maven coordinate strings and refer to Maven repositories. Once we've configured the required repo, we ask Bazel to use it with our current module by calling the useRepo method. As a result, our Java code can depend on the JUnit library. To sum up, we use the Maven extension of the rules.jvm external module to add a repo with some Java libraries to use them in our Java code. Okay? Now, it's instructive to see that all these repo manipulations are not some abstract things. We can actually look at them. We go to excluded directories in our project view and find all the configured repos. This one was created by our request and provides JUnit with everything it depends on. We've got so many repos because of the transitive dependencies. It's not that easy to build a trivial Java project, you know. By the way, we can also find Java dependencies in the traditional external libraries meta folder. The Bazel plugin populates it for us. Alright, let's look at how we describe what we actually want to build. Remember, a module is a unit of dependency management in Bazel. A package is a unit of the building process. We have two Bazel packages here, one for source code and the other for tests. We can identify them from build.bazel files. These files can also be called just build. So, a package is a folder with source files that has a build file in it. A package includes all the subdirectories except those with their own build files. Let's explore the build file for our main package. The first call here loads a specific rule for building Java binaries from the rules Java module. In build files, we can use some global Starlark methods, but we need to explicitly load anything specific. Then we have a package declaration and set a package visibility. We'll need to access the class from this package in tests, so it must be publicly visible. Finally, we declare a Java binary. This Java binary rule will instruct Bazel to collect all the Java source files in this package and build the main executable jar file from them. Let's mention two more things here. First, we can run the binary right from this file. Second, we can run it from the list of targets in the Bazel tool window. Bazel rules, like Java binary, have outcomes called targets or build artifacts. If we want to run an executable, we need to build it first. And the primary thing Bazel is responsible for is to come up with a minimal set of actions that need to be executed to produce the required artifact. Alright, here is a build file for a test package. The most important thing here is how we specify dependencies. We need two things to run tests: the class we are testing and JUnit. The first dependency comes from the neighboring package of the same repo. The second one comes from the Maven repo we've described earlier. Let's open that repo definition in a split window and compare. So, Maven is the repo name. JUnit is constructed from the Maven coordinate string. Now, let's run an experiment. Suppose we want to avoid ambiguity and call this repo differently. For example, test.deps. We should rename it in 3 places: in Maven install, in use repo, and in dependency link in Java test. Resync changes. Let's also rerun tests to make sure that we don't break anything. Good. What about repos in excluded directories? Here we are with test.deps. Yet another experiment. What if we want to go to a definition of JUnit's assert equals feature? IDEA sends us to the external libraries meta folder, but look, there are no sources. So we see a decompiled class. Not good. Any ideas on how to fix this? The first thing we need to decide is whether it's about build process, and then we should search for a solution in build files, or a dependency configuration, which means going to MODULE.bazel. In Java, jar files can include sources, but this is optional. So we just need to ask our Maven extension responsible for Java dependencies to fetch the jar files with sources. Easy. Let's add the fetch sources parameter to Maven install tag. Resync. Voila, the sources we need. To complete our understanding of modules, repositories, and packages, let's restructure our project. We'll move the current app to its own folder, add one more package with a library hosted in the same repo, and then make the app dependent on this new library. We'll be checking the Bazel configuration on every step to make sure that the transition goes smoothly. Let's start. Create a new directory. Move the source folder inside. Resync. Well, there are issues. We've changed the location of the main package, so the dependency in test is broken now. Let's fix it. Fortunately, the auto-completion helps to set the correct name. Resync again. Good. Next, we add a new Bazel package mylib, create a directory for a library source files, add a Kotlin file. It belongs to a package. Let's add a simple function. And let's also move the build file closer to the actual sources. It's empty for now. Alright, now to the Bazel configuration. We need to teach Bazel how to work with Kotlin. You already know that there are 2 steps here. 1. Providing necessary dependencies in MODULE.bazel. And 2. Specifying the rule for compiling a library in the build file. How do we know which dependencies to add? Well, let's switch to a browser and go to registry Bazel build and search for Kotlin. This one looks exactly like what we need. Copy the line and paste it in the MODULE.bazel file somewhere here. Resync. Now we need to set rules in the build file. We'll load the rule for building Kotlin library for JVM, define the library itself, and let's not forget to add a package directive to set public visibility, so we can actually use it in the application. Resync. Look, we've got a new target here. Finally, we need to add this library as a dependency. Let's copy the target label, go to the apps build file, and add depth argument for a Java binary. Resync. And of course, we want to use a hello function from a library. mylib. Nice! IDEA already knows about it and auto-completes a library, imports, and the function name for us. Let's run. Hello from Kotlin. What about go to definition? It also works. By the way, we can find the final executable in excluded directories and run it from there as well. At the beginning of this video, I mentioned that Bazel is supposed to be used with large monorepos. Here is the problem. Every single developer is usually interested in a small part of that monorepo, a specific subproject or a small set of them. With the IntelliJ IDEA Bazel plugin, we can configure a project's view to ensure that we see only relevant parts of the project. A default project view includes the whole project. Let's copy the .bazel project file to the root folder and then make another copy for a Kotlin developer who is only interested in the Kotlin library. So, our directory of interest is mylib. We need all the targets and all the subdirectories. Let's reload the project view from this view. Great, there is only one library target. The other directories are gone. Of course, we can still find them in excluded directories. Also, external libraries don't have JUnit that used to be here. We have only the Kotlin standard library. Here is the idea. The Bazel plugin hides everything irrelevant both from us and the IDE. As a result, IDE will work faster, so developer experience for huge monorepos can be greatly improved. And of course, we can go back to the full project view. We just need to load the project from the original project view file. This is all for the first part of this Bazel series. Next time, we'll talk about Bazel labels, how to construct them and where to use. We'll cover in great detail Bazel rules, actions, and targets. We'll also discuss the Bazel evaluation model. It's impossible to use Bazel without understanding of what happens when. But the most interesting thing we'll talk about next time is how to write your own rules and how to debug them with the IntelliJ Bazel plugin. See you next time, and please subscribe to this channel. Bye!